Today we'll start with the first experiment using the WLAN toolbox, that is IEEE 802.11ax channel modeling. The learning objectives of this experiment is to create a single user high efficiency format configuration object and initialize the transmit parameters for the HESU format of IEEE 802.11ax standard, to configure a TJX channel of 20 MHz bandwidth, to pass a waveform through the TJX channel, and to obtain the path gains of every individual multipath to obtain the complex baseband feeding coefficient, to obtain a channel impulse response for model D delay profile. Model D is a typical office enterprise scenario, and to obtain the statistical distribution of the channel amplitude or the envelope. So before going to the simulation part, let's try to understand some of the basic concepts in wireless communication. The mobile or indoor radio channel is characterized by multipath reception. That is, the signal arriving at the receiver contains not only a direct line of sight path, but also a large number of reflected signal components. Depending upon the density of scatterers, the signal will undergo different levels of fading. The channel fading can be mild, moderate, or severe. There exist different models for statistical characterization of the channel. In communication theory, Nakagami M distribution, relay distribution, and Rayleigh distributions are commonly used to model the scattered signals that reach a receiver by multiple paths. Depending upon the density of the scatterer, the signal will display different fading characteristics. Rayleigh and Nakagami M distributions are used to model dense scatterers, while Rayleigh distribution models the fading with stronger line of sight. So the basic model of relay fading assumes a received multipath signal to consist of a theoretically large number of reflected waves with independent and identically distributed in phase and quadrature amplitudes. But Rayleigh PDF cannot model severe fading conditions, and hence other fading models also must be explored. One such model is a Nakagami M fading model. So Rayleigh distribution is a special case of Nakagami M PDF when M equal to 1. A set of channel models and Pathloss models were created during the development of 802.11n standard. Due to the nature of the typical WLAN deployments, the propagation models were developed based mostly on indoor measurements. The channel models are composed of impulse responses for a range of indoor environments. There are 6 such channel models, each with a different impulse response corresponding to different indoor environments. An overview of these channel models can be seen in this table. So the channel model A is a flat fading relay model and is not applicable to a wideband system like 802.11. This channel model was included for its utility in analytical modeling. The most commonly used channel models are channel model B, channel model D, and channel model E. These 3 models are very largely used to compare proposals during the development of the IEEE 802.11n standard. These were also used for physical layer packet error rate performance. If you see, compare these channel models, the number of taps, if you see, for example, channel model B is a 9-tap model, channel model D is a 18-tap model, and the RMS delay spread is also different for different model. The propagation scenario for channel model B is indoor residential, example intra-room or to model room to room. Channel model B can be used. Channel model D is typical indoor typical office environment, for example, sea of cubes, a large conference room, etc. The model E can be used to model indoor large office or warehouses, for example, multi-store office, campus, small hotspot, etc. So one more thing to note here is the breakpoint distance. If you see for the channel model D, it is breakpoint distance is 10 meters, and for model B it is 5 meters. For model E it is 20 meters. The K factor, for example, the LOS K factor. The K factor here you can see it is applicable only for the tap index 1 in the LOS mode of propagation. And the K factors for all of the taps are 0, and for NLOS again the K factor is 0 after the breakpoint distance. So this, for example, this parameters is shown for model B and D. The breakpoint distance for model B is 5 and 10. The slope before breakpoint distance is 2 and after breakpoint distance it is 3.5. So here D is the separation between the transmitter and receiver in meters. LFS is the free space path loss in decibels. DBP here refers to the breakpoint distance in meters. For all the channel models, LOS conditions are used before the breakpoint, and NLOS, there is a non-line of sight propagation, is used after the breakpoint. The ration K factor, what we talked about previously, is the ratio of the power of the LOS component to the diffuse component is the ration K factor. So the distance between the transmitter and receiver determines whether the channel should be modeled as LOS or NLOS. For a LOS channel, yeah, this is the ration K factor. And for LOS channel, the K factor only applies to the first tab, as I told you earlier. And for all other tabs, the K factor is 0. And for a non-LOS channel, the K factor for all the tabs is 0. So now we are good to go to the simulation part. So this code obtains a channel impulse response for various delay profiles and statistically characterize the channel amplitude or the channel NLF. I have used WLAN HE SU config. This creates a single user high efficiency format configuration object. This object contains the transmit parameters for HE single user format of IEEE 802.11ax. This has various parameters that can be tuned according to your requirements. For example, the channel bandwidth, the number of transmit antennas, space-time streams, extended range. Here it is disabled. So 11ax supports a minimum bandwidth is 20 and it goes up to 320 megahertz. I have chosen 20 megahertz bandwidth. MCS support for 20 mega is from 0 to 9. MCS 0 is a BPSK modulation with coding rate half, which is more robust. HELTF type support is again of 3 types of different durations. I have set it to 1. Again, guard interval is set to 0.8 microseconds, and the PSDU length is specified as 100 bytes. After the transmit parameters are set, next step is to configure the TJX channel with 20 megahertz bandwidth. The carrier frequency default is 5.25. I have set it to 2.4 gigahertz. The sample rate is set. The path gains output port is set to true so that you get the channel path gains in order to plot the impulse response. The delay profile I have chosen as a model D, that is a typical office enterprise. The last scale fading effect is enabled. The path loss is enabled. The distance between the transmitter and receiver is set to 15 meters. Then you can also include the number of walls between the transmitter and receiver, and the penetration loss of single wall is set to 2.5 decibels. So if you see the path loss earlier, I mean, already have run the code once to have the result. At the end, again, I'll change some parameters and see what is the result. So for 15 meters and path loss enabled, it uses the breakpoint distance model as I told you earlier. For channel model D, it is 66.2 dB. Now, since I've had it additional loss because of the walls, you have plus 5 dB loss here. So now the data packet is created using the random number of bit patterns being generated, and this bits packet which consists of ones and zeros has to be converted into waveform before passing it to the channel. So this waveform generation is done using WLAN waveform generator, which accepts the data bit pattern and the configuration object, and the TX waveform is created. This TX waveform is waveform containing an 11AX HE single user packet. It is complex NS by NT matrix, where NS is the number of the time domain samples and NT is the number of transmitting antennas. Since it is a CISO configuration, what we are doing, NT will be equal to 1 and TX waveform is a column vector. Now this waveform is passed through the TJX channel, and I've already set the TJX channel properties. And TJX channel output is the received waveform, and also you get the path gains. I reset the TJX channel in order to create a new channel realization every time. Then the path the channel, you have info TJX channel, which gives information about channel filter coefficients, path delays, average path gains, and also the path loss information. So for model D, the channel filter coefficient size is 18 cross 40. It means the impulse response length is 40, wherein you will have 18 non-zero taps. So NH is 40, as I told. It has 18. The number of columns of channel filter coefficients is the number of or the length of the impulse response. Then you, as I told you, there are 18 non-zero taps. The path gains is obtained, and then you plot the impulse response, absolute value of the impulse response. Also, in order to obtain in order to characterize the statistics of the channel impulse response, I'm going to accumulate this channel impulse response in a vector called a matrix called CIR. So channel impulse response is 40 cross 1, but when I accumulate, since I'm going to run this for 5,000 times, the size of CIR will be 40 cross 5,000. That is the number of impulse response length into number of packets. Each row of CIR is an ensemble of a random variable corresponding to a particular channel tap. So now I'm going to collect the tap index is a vector. Say here I'm taking the fourth non-zero tap index, and the size of this would be 5,000. It is a number of packets you simulate, and it is now it's a random vector consisting of 5,000 random variables. It's basically the channel coefficient, fourth non-zero tap. So for at the end of the processing, then I'm going to plot the TX waveform and also plot the that is an input the waveform into the fading 11x channel and the waveform out of the fading 11x channel. As we have the only impairment which is done in this experiment is a fading. I have not added any EWG and noise in order to analyze only the effect of fading on the transmitted signal and to obtain the channel fading coefficients. Doubleland field indices gives the index values of different fields in the packet. For example, if you see here, LLTF, LLTF, LSIG, that is a short training field, long training field, and LSIG. This is the legacy preamble. So first 160 samples is LSTF, next 160 samples is LLTF, then around 80 samples corresponds to LSIG. So these first 400 samples is the legacy part of the packet preamble. Then RLSIG to HELTF, that is 321st sample to 800th sample is the HE part of the packet preamble. Then you have HE data, and the packet extension is 0 here. So now here I'm sketching the impulse response, the absolute values of the impulse response for the model D. And now here I'm trying to see what is the distribution of the channel fading coefficient considering the fourth non-zero tap index. So I make use of the histogram and then plot different. I've set the normalization into PDF. You can choose different colors. I'm fitting the distribution for Relay, Nakagami, and Ration, and see the data, whatever the observed data I have, where it fits to which of these three distribution. Then I'm going to plot them. I also save this file for future reference. If I run this, I've already run this. So first thing is this is the signal which is going to the fading 11x channel. This is a faded signal which is coming out. So here, if you see, this is the preamble portion of the packet which is standard defined. If you see, the preamble is also faded. Basically, this will be a BPSK modulated signal. And the second figure here is the preamble portion, which is enlarged. It's approximately 40 microseconds of waveform. This is a channel impulse response, the non-zero tap index. You have 18 non-zero tap indexes, but the length of the impulse response is 40. So the delay spread, if you see, it's around 400 nanoseconds. The tap spacing between one to the other tap is 10 nanoseconds. So you have 18 non-zero taps. This gives the histogram and the PDF fit. You can notice that this channel model was D and the distance was 15 meter and the channel tap index was 4. So basically it is NOL, non-line of sight propagation, because the breakpoint distance for channel model D is 10 meters and I've set it to 15. And also the tap index, what I have considered for plotting is fourth tap index. Here the Rayleigh K factor is 0. And hence when the Rayleigh K factor is 0, the Rayleigh PDF reduces to Rayleigh. And also if you see the Nakagami distributions parameters, mu is approaching 1. It means Nakagami M fading is becoming Rayleigh fading. When M is tending to 1, Nakagami reduces to Rayleigh distribution. Hence, for this simulation, all three are overlapping. So now, if I change, now this is NLOS, non-line of sight. If I change in the code, say if I set the distance to 5 meters, which is less than the breakpoint distance, I'll change this to 5 and also consider the tap index. There is a first tap index where the Rayleigh K factor is non-zero for channel model D. I think it is 3. Yeah, here. Now we'll see what is the result. So here the distance I have changed to 5 meters and the tap index what I have considered as first tap index. So it is a LOS propagation. So as we have seen or as we have discussed earlier, among Nakagami, Rayleigh or Rayleigh, which is going to best fit the LOS model, it is Rayleigh distribution, and we will see that. It takes some time. So coming back to this, whatever I was telling is about this thing. So the LOS K factor, it's applicable only for tap index 1 in LOS. For channel model D, it is 2. And LOS K factor for all other taps, for all the non-zero taps, it is 0. And if you go for NLOS, it is again 0. That is why when D is equal to 15 meter for channel model D, and if you had considered the tap index to be 4, all three distributions were overlapping. This is because when K factor is 0, the Rayleigh fading reduces to Rayleigh. And since the Nakagami M parameter was 1, the Nakagami was also reducing to Rayleigh, and hence there was hence all three distributions, fading distributions were overlapping. Now what is the change I have done? I have considered still channel model D, but I have set the distance to 5 meters. So the breakpoint distance is 10. It is less than 10, meaning I am in the LOS. And also I am now seeing the histogram or the distribution of the first channel tap index, non-zero tap index, first channel non-zero tap index. So here the K factor is non-zero. Therefore, we expect to see that the Rayleigh distribution is going to best fit the distribution of the channel feed. Yeah, as expected, if you see here, now I have changed this tap index to 1. Earlier it was 4, now it is 1. Now if you see the Rayleigh, Nakagami, and if you compare the Rayleigh fading for LOS propagation, the Rayleigh PDF is going to best fit the channel feeding coefficient envelope. So to summarize, Rayleigh distribution models only the non-line of sight signal components between the transmitter and receiver. Rayleigh distribution models both LOS and non-LOS. The Nakagami M distribution models a wireless environment with moderate to severe fading such as urban or suburban scenarios. Thank you.